Swayam Prabha. Digital India. Educated India.
I will keep this. We saw the ideal precon, that was what we were discussing last class. That is essentially the root moment is k beta, beta naught minus beta p. This is the ideal precon. Okay. If the precon value is this, it is ideal precon, then you already kept it at that, then there will not be any root moment, because root moment will be 0 value. That is the idea of in actual design. What they do is they will keep a little bit of precon angle, so that you relieve in the design, structural design, it is purely from a structural design point of view, you reduce the moment that comes at the blade root. Okay. Because these are all design features, plus they also have certain influence on the stability, because if you remember last class, because I am just going back, we wrote k beta into we substituted for beta naught and we got this equation 1 by, because this we wrote last time, beta ideal minus beta p. Okay. And you can replace that k beta directly, because that is again written in terms of we know omega bar r flap square is 1 plus omega bar non rotating flap square, which is IB omega square. Okay. So, what you are doing is you now subtract from here, this will be IB omega square into omega bar RF minus 1. Okay. So, you substitute this here. Now, everything will be in terms of over minus 1 and IB omega square beta ideal minus beta p. So, you see automatically whenever the flap frequency, rotating flap frequency is equal to 1, root moment is 0, you do not get any hub moment. Okay. Whereas, the moment you have a rotating flap frequency greater than 1, then you get a hub moment, but beta ideal is not equal to beta p. So, now you may have any frequency, but if ideal is equal to beta p, then you will not get any root movement. Okay. But it is not that you do not want to get any root movement. See, it is a very conflicting requirements. If you want to maneuver, you need to have root moment, because you want to generate moments. Otherwise, you will generate, later we will show, you will generate only the moment on the vehicle only by thrust vector. That will have some value, but if you want to have highly agile, you need to generate more moment, then you need to have hub moments from the rotor blades. But at the same time, you do not want the blade to have lot of root movement from a structural design point of view. On one hand you want a highly agile one, but on the other hand you do not want the structure to be very big. So, this is a trade off. Finally, that is why the design of rotating flap frequency to have a particular number is a very interesting and very important in the helicopter design. What flap frequency you will keep for your helicopter. Okay. Next, we will look at if you have the rotating flap frequency other than 1, what will happen to the phase difference between control input and the output. Because earlier when the centrally hinged blade, we said that the phase is 90 degree. Okay. Now, what will happen is, if this frequency is more than 1, that phase difference will reduce. It will not be 90, it will be less than 90. Okay. That means, we will see what that value is. We will derive only for the hover case, but you will find that if you restrict your case to hover, the relationship between this, I am writing it from the notes which I wrote last time. Okay. And then RF square minus 1 divided by gamma over 8 minus beta 1 c, sorry, beta 1 s equals theta 1 s. This is the relation which is reduced from last time I wrote the long expression. From there, if you put mu 0, okay, you will get this expression, particularly in hover case. We are looking at hover first. You can solve for beta 1 c and beta 1 s from these two equations, because your control input is this and this. Okay. Now, if you write that, I will just briefly see from these two equations, you see that there is a coupling between longitudinal and lateral, in the sense, if I give theta 1 c, I am having these two. If omega RF, rotating flap frequency, is other than 1, if it is 1, you got this directly, because this we got earlier. If it is not, you are introducing coupling between longitudinal and lateral motion of the rotor disc. And if you can solve this, I am just writing this result, that is beta 1 c becomes minus theta 1 s plus minus 1 over gamma over 8 theta 1 c divided by 1 plus omega bar r f square minus 1 over gamma over 8. Okay. And similarly, beta 1 s equals theta 1 c plus omega bar r f square minus 1 over the denominator is same, okay, minus 1 over gamma over 8. Now, this is the movement in hover itself. I am changing my flap frequency other than 1. So, I am coupling now. Okay. Whereas, when the flap frequency is 1, you know that theta 1 c gives you beta 1 s, theta 1 s will give me beta 1 c, that is all. But most of the rotors have flap frequency other than 1, that is actually more than 1. Now, using these relations, you can find out what is the phase difference between input output, okay. And that I leave it to you as an exercise, because if my input is theta equals theta bar cosine psi plus psi naught, and my output I call it beta bar cosine psi plus psi naught minus delta psi. So, this is my input, okay, because you know that theta naught is different. We are looking the cyclic inputs affect my rotor tilt, but how much it affects, it is like this. If you pilot gives an input in the longitudinal direction, thinking that he is tilting the rotor disc like this, he wants to go forward, what he will do is he will also start rolling. Not only he will do pitch, he will start rolling, he will start moving left or right depending on the coupling. So, that means the two axes are not independent, they are coupled, which is difficult to fly when you really want to go in forward direction. You will start going in some other direction. If you want to give pitch, you will roll, but you will also pitch. It is not that you do not pitch, you will roll. And particularly when we, I hope there will be some time for analyzing the flight dynamics, the inertia of the vehicle is different in pitch direction and roll direction. Pitch it is larger, roll it is less. Now, if the inertia is less, what will happen is, if pilot gives an input for pitching down, actually he will roll much more than what he intends to do in pitch itself. That is because of the less inertia in the roll direction. Now, this coupling is very difficult for the pilot to fly. So, what do they do? Because one input gives me two outputs basically, one intended, another one unintended. That means, I have to go either compensate for that. Okay. This is where the flying requires skill. Now, you can have automatic flight control system, etc., many things, but that will aid the pilot to assist him slightly. Okay. This is one of the key, I would say, the difference between an aircraft and the helicopter, one of the key in flying the machine. Now, you see, if the input is, I can write theta 1 c is what, theta 1 s, similarly beta, this is the phase. Okay. Using these equations you solve, I will just write the answer, okay, because that is algebra. So, which you can try yourself. That is the input. Theta bar is actually the magnitude of input, that is under root, and beta bar is beta 1 c square plus beta 1 s square half. That is basically the amplitude of your input. Okay. Because you can see, if you expand this, theta bar cosine psi naught, cosine psi is time varying, that means theta bar cosine psi naught is basically theta 1 c, okay, because psi naught is some number. Okay. Now, the phase is actually tan delta psi is gamma over 8 minus 1, and this can also be written as delta psi is 90 degrees minus theta, which is 90 minus tan inverse minus 1 over gamma, because you just put 90 minus, okay. That way that ratio gets changed, because you can write this itself as tan 90 minus theta, just, okay. Then you know this will be 1 over tan theta, okay, right. That means tan theta is omega bar RF square minus 1 over gamma 8. So, that is how you just because normally you write the phase is 90 degree when this is 1. Now, you see two parameters are controlling. One is the flap frequency, another one is the Lock number. Okay. Lock number is, you know, that it is the ratio of aerodynamics over inertia of the blade. So, both of them influence the coupling. Now, just for some number, if omega bar RF is 1.15, okay, and gamma is 8, then delta psi will be 72 degrees, and your beta bar by theta bar, that is the magnitude of the input to the tilt. This actually is 1 plus omega bar RF square minus 1 over gamma over 8, okay, whole square power minus half. Usually you will find this reduction is not a lot, that is the magnitude of the flap and the input, there will be slight change of 5%, because if you take it as 1 minus 1 0, so beta bar is theta bar, okay. But if it is 1.15, you take a square, you subtract 1 gamma 8, you take again square and then bring it, it will be about 5%, 6% change, whereas here this change is substantial. So, what happens is, if pilot gives a longitudinal, he will roll. Now, what do? Because the pilot, how this is done is, there is some control rigging, they call it control rigging. That means, pilot will still move his stick forward, but the input that goes to the blade is adjusted such that if you have the rotor disc, if this is x, this is psi, this is 0 degree, 90 degree, 180 and 270, and you are flying forward, velocity is coming. Just I am saying, because forward flight also will change, we are doing just hover case, okay. If I here theta 1 s, what it will do is, it will go until here, this will go like this. So, what normally done is, when a pilot gives, he will give an input somewhere here, so that this rotor disc tilts. So, he will go forward. So, they try to reduce the coupling. That rigging is done in the mechanical arrangement of your control rods. Now, you imagine that design, the layout depends on what is your flap frequency. Okay. So, it is everything is linked, even your design, layout, many of these things linked to flap. Otherwise, you are actually increasing the load of the pilot, because he still has to do a lot of control. Okay. Now, this face angle, is it constant? That 72 degrees, is it whatever we got for this, is it fixed? No, it may vary with forward speed, okay. But control rigging is done for one, that variation is not very large, that is why it is done at one value and then just leave it. After that, pilot has to fly. If there is a coupling in some other forward speed, then he has to adjust. Okay. So, the flying he goes through a training. So, the key aspect is coupling between longitudinal and lateral. So, when now you imagine, if you want to do, you have done in aircraft, I think if you have gone through the first level course, longitudinal dynamics separately you do, lateral dynamics you do it separately. But in the case of helicopter, because most of the people who are trained is aircraft first, even here, okay, let me analyze the longitudinal dynamics of the helicopters, even though it is not right. Okay. You have to analyze the full helicopter. So, industry, for ease of understanding, okay, you can do a little bit of the decoupling, but otherwise it is not possible to decouple the full longitudinal lateral degrees of freedom. So, you have to solve the full 6 degrees of freedom, all coupled in the flight dynamics. Okay. Now, control becomes more complex, because usually when you decouple all these things, you try to understand each subset and then make some design modifications such that the vehicle is good. Here, if you do something in one, it is going to affect another thing. So, that is the coupling plays a dominant role in helicopters. How do you reduce it? Reduce it, but if you reduce it, it becomes, you say that why you want to have, make it, this is 1, that is wonderful, okay. But then the problem is, now what we are going to discuss, what happens to the hub moment, okay. Because till now we have studied thrust, side force, longitudinal force and the torque. I said we keep the hub moments for a later thing. Now, let us look at the hub moment which arises due to the flapping aerodynamics, okay. Flapping motion, I would call it flapping motion, because you have to take the inertia also. Now, how do you get the hub moment? So, this is the, we have our model is a centrally hinged blade with a spring, okay. This is beta, okay. One way is you calculate the, like we did, inertia force, aerodynamic force, integrate and get that. Another way is, hey, what is the deformation of the spring? Okay. Deformation of the spring is, we said k beta into beta p. This is the moment due to the deformation, and that is acting at the hub. Now, you see there are two ways of calculating the hub moment, even shear also. This, if you do vibration, you will learn later. I can get the aerodynamic load, inertia load, integrate the whole thing, come to the root, give that as a moment. That is one way. Another way is I look at what is the root deformation, I just take that, multiply by the spring constant. In this case, it is much easier. Suppose if it is a flexible structure, okay, I want to know the root bending moment, root shear force. How do you get that? Okay. I am just throwing it to you to think about it, but here we take only this, because there are two ways of, see, it is like this. I am just giving you, I am deviating a little bit. You take this a cantilever beam, you have learned some loading. I want to know what is the bending moment and shear at the root, okay. Maybe shear force, some bending moment. How do you do? You integrate, you will get that, you put it. That is one way. That means you are integrating the loads. But you also know bending moment is E I what? Okay. This is also, and the shear force, you have another d over dx of maybe E I. Okay. This is a shear force, simple. Now, if you know W, you can get this also at any location. You take the slope, you take the moment, you know, whatever. So, this is another way. That means you solve for W, you solve the deformation. After that, put it. Okay. One is take the applied load. Please understand. Now, you apply the load, you integrate the load, and you get the bending moment and shear at some section. Another one is you solve for the deformation and then take whatever the standard. In aeroelastic problem, what happens is the load is a function of deformation. Please understand, the load, what applied load, what I put it is a function of deformation, how much it deforms. That means what you have to do? You have to solve for deformation to get the load, but you need to know the load to get the deformation. Okay. So, this is an iterative process. So, usually we do not go and calculate bending moment and shear by this approach, because of the simple reason you are taking secondary, all approximate you are doing numerically. Whenever you do differentiation, you may have error. So, when you want to get the loads, you simply integrate the aerodynamic and inertia. But if you want to get the deformation, because you also need to know the deformation, then you have to solve the full problem. Okay. So, it is like here what we are doing is, we are not integrating the loads like what we did for thrust and other things. We simply say what is the deformation at the root, it is easy for me, but only thing is I must know beta exactly. Okay. Here I know that I am just assuming that beta is known. So, I take it, I take this is the flap moment acting at the hub, okay, at any time, because beta is a function of psi. So, now I want to get, this is my rotor disc, this is my helicopter, and this is my y axis, this is my x axis. The flap moment, when the blade is here, the flap moment is about this axis, right. About the, this is x1, this is y1, this is my flap moment, which is this. So, I must take component of the flap moment along y and x direction, that is the body hub direction, and then I must add the values due to all the blades and take the mean value. Okay. That way I get a hub moment. What we did was, we get all the forces in one blade, then we added all the blades, assuming that the blade behaves the same way. Here also it is the same thing. Now, let us write this quantity, that is the moment, flap moment. I will write it flap moment. Okay. IB omega square omega bar RF square minus 1 into beta minus beta P. So, I am converting the spring stiffness directly in terms of flap frequency, rotating flap frequency. Okay. This is a modification, this is just because you know that what is K beta. Now, using this, I will go get my moment, because this is my psi. So, this angle is also psi. I take along x and y. Okay. What is the moment? So, I will have my will be my moment here, pitch moment, and mx will be my roll moment. This is mx, this is my. Okay. In the hub system. So, my my becomes, please understand, I am now doing a m, which is the flap moment, into okay, this is pitch moment, and similarly roll moment mx n over 2 pi integral 0 2 pi m, this is roll. Please understand, these are at hub. Because you know that the flap moment, how much the spring is deforming, means what is the force. This is very similar, simple problem. You also, you know that if you have a spring mass, whatever force etc., everything acting here F, M, K, if you know what is the force that acts, it is just Kx, that is all. Same way, here is the force, here it is the moment. So, K beta times the deformation, and K beta is replaced by this. Now, you put it here, and you know beta is beta naught 1 c cosine psi plus 1 s sin psi, because we are truncating rest of the quantities, we are not considering only first harmonic. Now, you substitute here and then integrate the whole thing. You will find beta naught cosine psi, beta naught is a constant, it will go to 0, and then beta 1 s sin psi cosine psi, that is again sin 2 psi integral, that is also 0. Okay. What you will have is only beta 1 c, that m is this expression, you are substituting for beta this expression, you will find only beta 1 c will remain for pitch moment, and for roll moment only beta 1 s. Okay. That expression is, I will write it here, because now you non-dimensionalize it, maybe I erase here. Okay. You non-dimensionalize your moments, that is CMY, like CT you will put my over rho pi r square omega r. Okay. And my you will get what? That is minus n over 2 IB omega square, because here I am just substituting this quantity and integrating. You will have omega bar RF square minus 1 beta 1 c over rho pi r square omega square r square r. Okay. Now, this quantity is you knock out these terms, and here n by 2, what is that? What do you have? There will be minus n I b over what is that 2 rho pi r square r into omega bar r f square minus 1 beta 1 c. What you do is you pi r square, you put n c multiply by r, c r in the numerator, denominator you multiply by again c r. So, you will have 2 pi r square, you will have c r, and then what is that? No, c why no there is a then r square r, right, am I right? Oh, sorry, right. Now, what you do is, oh, sorry, okay, I will put the row. This sigma. So, you anyway you will have this term, you will have minus sigma rho c r power 4, right. Where is I? Oh, yeah, sorry, okay. Rho c r to the power 4, you multiply by a lift curve slope a and divide by a, okay. Then this factor is rho a c r to the power 4 over I b, this is gamma, okay. So, you will have minus sigma a over 2 gamma, sigma a is there, this is gamma, and 2 into you will have omega bar r f square minus 1 beta 1 c. Okay, let me simplify and write it. So, your C m y becomes minus sigma a over 2 omega bar r f square minus 1 divided by gamma over 8 beta 1 c. That is all. Okay. Sorry, not 8, okay, I am sorry, gamma. Okay. Similarly, you can write for mx. Here what will happen is beta sin psi. So, you will kind only 1s will come. So, that I just write the expression. Okay. So, your beta C m x becomes sigma a over 2 omega bar r f square minus 1 over gamma beta 1s. Okay. These are my hub moments. Now, there is a little thing further to this. Okay, we got the hub load, all the 6 components. This is what I gave you in my notes, the 2-page. Okay. If you know the value of These are all rotor configuration. Omega bar RF square flap frequency is a rotor characteristic, gamma is the rotor. Only thing is depending on your beta 1c or beta 1s, how much moment you are generating at the rotor hub due to the rotor. Now, how much you generate at the fuselage CG? Because fuselage CG, you will get the hub forces, they will also get transformed into the fuselage CG. Hub moment also will get directly transformed. What is the relative order? If you look at that particular part, there is a slight derivation, because that is again highly approximated. Please note, because you know the CT, you know CH, you know CY, okay, assuming that wherever is the CG in your fuselage, very simplified form I will show that diagram. Moment about the hub center, because these are all for controls flying, you need to know that value. You assume that the CG is here, rotor hub is at a height h, okay. Just I am putting it right on shaft, it need not be straight on shaft, it can be anywhere, okay, a little displaced. Those things will come when you do the actual problem. Now, you have a hub h longitudinal force, mx which is the roll moment. Similarly, you have y which is the side force, which is the my which is the pitch moment, and thrust and the torque. These are the hub loads due to the blade operating condition. But what happens to this? If you look at this, because I have written some form to come to this, okay. See, if you want to know the pitch moment, the thrust is what? Directly passing through the CG, because I am saying CG is right on the shaft and thrust is always I define on the perpendicular to the plane of the hub, and it is true, it is not going to give me any moment. But what will give me moment is the h and the y, side force and the longitude. Side force capital H into this height, that will give me a pitching moment. Similarly, the y force onto this height will give me a roll moment. So, at the fuselage CG, I generate moment due to two sources, one direct moment, another one is due to the forces. But this particular thing which I have written here in hover, see it is very interesting. In hover, we can reduce it, but we make again assumptions, that is what I am telling you, lot of assumptions are made. In hover, if you look at what is my longitudinal force coefficient CH, because we got that expression last time, that long one which I gave you that sheet. You can say approximately that is thrust into beta 1c, approximate, because you have to replace theta 1c is beta 1s, that kind of a relation you have to use it to get that approximation. Okay. It is again I am telling you, this is obtained from your that page which I gave you, that printout. Now, if you use these expressions and then calculate net moment at the CG, please understand, net moment at CG, one is hub moment, another one is due to thrust, because you see it is converted, that h and y are converted in terms of CG. This is the in plane hub loads. Now, if you use the omega RF is 1.1 or 1.05 whatever, or 1.15 is a slightly higher value, you will find this value is much higher than this value. Okay. If you use, so this is direct hub moment, this is through tilt of the thrust. Okay. So, you have two sources. Due to tilt of the thrust vector, the moment you get is some, but direct hub moment is sometimes 2 to 4 times greater than the effect due to tilt, because CT value you can substitute, sigma you substitute, A you substitute, H over R you take, you will find. Now, you see if pilot wants to do a good maneuver, which moment is good? Suppose if you make my flap frequency is equal to 1, that means this term is gone, I do not get any hub moment. He has to fly only with this CT, only by thrust tilt. That is why in the helicopter you do not go to 0 thrust condition. Okay. That is the inverted loop. When he goes 0 G, 0 G means 0 thrust, that means he cannot generate any moment, that means he will lose control over the vehicle. That is why helicopters, particularly the two bladed where it is centrally hinged, you do not have any moment, you do not fly low G because you do not have the moment. That is why they try to put some spring so that increase this, the control. But then if you keep on increasing the flap frequency, it will become highly sensitive, because any small change immediately it will start rolling. Now, this is the trade off, what you would like to have, whether you want a sluggish but stable vehicle, or you want highly sensitive, but highly sensitive means again it is subjective. So, when they go through the flight, they always ask the pilot. So, pilot's opinion plays a major role in, then they actually drew some diagrams in which all the pilots, different pilots, then they came, oh this is convenient, this is okay, I can handle it. But then experienced pilot will be able to, his opinion will be different from a new pilot. Okay, once as you gain experience, he will say yeah, it is okay, I can handle it, but new pilot will say oh, it is very difficult. So, these are all the trade offs which one has to, finally they will say all right, let us decide on some combination of, in the sense the flap frequency gamma, how do we play? Flap frequency is most dominant, usually it is kept, you will be surprised, omega bar RF for articulated. Okay. Articulated rotors, it may be 1.02 to 1.03, somewhere around that. Okay, 02, 03, maybe 04 is a slightly higher. For hingeless, okay, omega bar RF is 1.07 to 1.1, somewhere around that. Now, you see articulated rotor, because you have a hinge, but you do not have a spring. So, the model is little different, that part when we do the next section you will learn. You see the flap frequency difference, this is a high flap frequency. That is why I am saying I have written up to 2 decimal points. Industry will calculate, you will be surprised, they will want to go to at least 3 decimals, 2 to 3 decimals in flap frequency. Why? Because if I square it, 1.07 becomes what, 1.14, okay, approximately. You subtract 1, okay, that means 1 is gone, the leading term is gone. So, what is left is only 0.14. So, if whether it is 1.15, 1.05, 1.07, those numbers become, that 1 is not dominant now. Okay. So, even if you change your flap frequency little bit, okay, your hub load is changed by substantial. So, you will see very interesting, the change in flap frequency here, what is it? It is almost 5 in 100, right, that is what 5 in 100, 0.5%, right here. Whereas, if you substitute the square and then get the hub moment, that is 1.02 square minus 1, this factor will be, this is what 0.004 to 0.04, right, 0.04 approximately, whereas here 1.07 square minus 1, this is 0.14. Three times the change, whereas flap frequency changes you say only 5%. Okay, I have changed my flap frequency by 1%, 2%, but I change my hub loads like 3-4 times. Follow? This is a very, very critical thing in the helicopter. Up, another goes down. So, you have to integrate from minus R to plus R. That is why that stabilizer bar part you have to do that. Okay. This is for each blade is independent. It is not that the other blade is dependent on the motion of the one blade. If you do that, that equation will slightly change. Okay. So, is it clear? Because you find flap frequency is a very, very dominant parameter, really influencing. So, industry spends enormous time, because in deciding and in going through the iterative thing, several design. Now, imagine you are actually making a blade, composite blade with a hub design, you must know the flap frequency to the third decimal. Usually they will say 1.092 or 93, something like that. You may wonder what is the third decimal doing, in engineering thing you will say it is all right. Even 1.09 or 1.1, it makes a lot of difference. Okay. So, is a 0.9, do not round it off to the next decimal, only for flap. That is why I am saying in the helicopter certain things are really critical. Then the criticality of each feature gets changed or reduced just for the blade alone. Okay. So, the design, you will be surprised, they may do the blade frequency calculation almost every day. Like if you are an engineer, you keep doing it, change some small stiffness change, okay, go rerun the whole program and then get the flap frequency. So, every day your job will be get the flap frequency and of course, lead lag, keep plotting, that is all, because that is very, very important. You may find what is that I am doing every day, every same program I am running, change some small number, get it, okay, but it has to be done that way. Finally, they freeze it, okay, this is the number, but now you see that is a theoretical calculation. Then you do experiment. Of course, experiment what you get, you take it, because you can't do much about it, you can't change anything. Okay. So, in the case of course, ALH, it is around 1.093 or 91, something like that, flap frequency, which is high. Why it is high? They say now you find that when I have my flap frequency high, I get a good control moment, but at the same time that means I am transferring lot of loads from the rotor to my fuselage. So, I will transfer more vibration also. So, if you have less small flap frequency, the load transfer is less, vibration also may be less, and but control is also less, agility is less. Now, what is the trade off? Okay. This is where the design goes into several iterations, and once industry has gained experience in a particular design, they will stick to it. Okay. because they know that this kind of design will do this effect and I know the sequence. All right. Now, with this I close the flap, simple flap motion. Next starts the trim, but that I will start in the next class, because I want to show one small demo. How, see, you have a blade, of course, it is a centrally hinged, how it will respond, because we said if I change some body motion, it is rotating, how fast or how slowly it will respond. That is why I thought I will show you a small video clipping, not video clipping, sorry, actual model. We have a model and that will be able to see, seeing is believing. Okay. I will remove this. What? Is it here? This is better, huh? Okay, now you rotate what you can. So, now this is spinning. If I tilt, you see, it takes slowly that, see, this line, the rotor disc, see, rotor disc is perpendicular to the shaft. If I tilt the shaft, it will not immediately come, you see, it takes time to come. And this particular delay, please understand, see, if I tilt, see this delay takes time. This does not have any aerodynamic, only two masses, just like a stick which is spinning. Okay. This is called the stabilizer bar. Now you see this has an inertia, it keeps rotating. So even if I tilt my shaft, it takes some time for it to come to the other position. This gives a feedback in my, now you have to put the, now you put the just a blade, you see the response. No, only one of them, it will be very fast. There it takes some time for it to come. Now you are actually, it is only inertia in that case. Now you add aerodynamics, that is like you are having the airfoil. If I tilt, you see it will immediately come. The time it takes for the rotor to respond is very quick, particularly in flap motion. That is why even though there is a lot of dynamics involved in this, the pilot will usually feel that he gives an input, it does not mean that okay, it takes a lot of time to tilt, or there is no, that sluggishness will not be there, it is very quick, you will feel that it is acting quickly, response is pretty good. It is very interesting, that is why, because this is like a gyroscope, please understand, right now what we have done is we are just spinning it. Yeah. Now what we did was we had put two aerofoil shapes, just they generate lift. Now you see, you rotate it, see if I tilt now, see it is very quick, whereas in the other case it took some time to, the aerodynamics alone influences the response. You can actually write a equation for this type of dynamics. Okay. Just a rod, you are just rotating and it has to do this response, what is the delay. But if I put to just aerodynamic lifting surface, very simple model, whatever we have done, how quickly it responds. And the same thing happens in the rotor blade, because it is a rotor blade, you give an input, it quickly responds. So it does not take lot of time, pilot gives, it will not do slowly, it will be pretty fast. Okay. Now we were, I will just briefly mention about the, I think this is enough. the trim part. So, I will describe the trim the next class. What is the procedure? It is only the procedure and final results I will show for a general helicopter system. After that, the subject can take in different directions, okay, because it can be only blade dynamics. Please understand, not flap dynamics, blade dynamics. That means you do flap, you do lead lag, you do torsion, and then you do combined, coupled. That is a one direction of work. Another one is you take only the flap, but include fuselage motion. That means coupled blade fuselage dynamics. You follow? And that has its own set of problems, like you have flap motion coupling with the fuselage, lead lag motion coupling with the fuselage. Each one has its own stability problems, okay. And then flight dynamics is rotor and the fuselage. Now, you see, you can pursue your course or the lectures in various directions, because everything is going to be complicated, okay, because it is not that I can write an equation. Only for blade isolated flap I can write, isolated torsion I can write, that I will cover after the trim part, okay. Then we will, it is pretty much like what are the various types of problems you face in helicopters, that is all. It is a mostly descriptive with some mathematics, but you can't derive the equations because it is too much for us, okay.